Hello everyone and welcome to this lecture on artificial intelligence in electrical engineering. I am Dr. Gauri Shankar M, Associate Professor from the Department of Electrical and Electronics Engineering at MCE Hassan. In this session, we will explore how AI is transforming the electrical engineering landscape. The scope of applications, the goals behind adopting AI, and why it has become essential for modern power and automation systems. Framing AI problems in electrical engineering. To apply AI effectively, we must understand the types of problems we deal with in electrical systems. We commonly encounter classification tasks like identifying relay or line faults. Regression problems help forecast demand or predict equipment behavior. Control problems involve designing adaptive strategies for inverters or automatic generation control. We also face anomaly detection challenges, sensor drift, cyber intrusion, hidden failures where early detection is critical. And finally, optimization, which supports placement, tuning, and cost efficient operations. For each of these problem types, different machine learning and AI algorithms such as support vector machines, convolutional neural networks, long short-term memories, reinforcement learning, and meta heuristics are applied depending on the system needs. Next, key assumptions underpinning AI methods. AI does not work magically. There are foundational assumptions. First, the data used for training must represent real world operating conditions. Otherwise, bias becomes a safety risk. Many models assume stable behavior, but power systems are dynamic and non-stationary. Several algorithms assume independence of data points, but sensor networks are often highly correlated. Model complexity must be balanced with generalization. Overfitting is a major challenge in engineering datasets. And finally, cost and latency matter, especially for real time control and protection, where decisions must be quick and reliable. AI techniques, a practical taxonomy. AI methods applied in electrical engineering can be organized into a practical taxonomy. We have rule-based system, widely used for protection, logic, and expert systems. Probabilistic methods like Bayesian networks help in uncertainty modeling and state estimation. Machine learning and neural networks, including CNNs and LSTM, help in forecasting and pattern recognition. Reinforcement learning enables adaptive control and policy optimization. Evolutionary and meta-heuristic methods like genetic algorithm, particle swarm optimization, and differential evaluations are used for placement and tuning problem. And hybrid approaches combine multiple paradigms such as neuro-fuzzy systems to overcome limitations of individual methods. Next, soft computing versus hard computing. In electrical engineering, we often differentiate between our soft and hard computing. Hard computing uses deterministic, mathematically exact models like classical control, otherwise linear programming, great for certainty and provable correctness. Soft computing, on the other hand, emphasizes uncertainty and approximations. It relies on methods like neural networks, fuzzy logic, and genetic algorithms, ideal for noisy, nonlinear, and complex systems. Understanding when to use each plays a crucial role in designing intelligent electrical systems. When to use soft computing in electrical systems. So, when should we choose soft computing? First, when data is noisy or incomplete, fuzzy system excel here. Second, when system experience strong nonlinearities that are hard to model analytically. Neural networks help capture these behaviors. Third, when real-time adoption is required. Reinforcement learning and adaptive controllers are suitable. Fourth, in multiple multi-objective scenarios like balancing cost, efficiency, and stability. Meta heuristics work very well. And finally, when explainability is important, neurofuzzy hybrids can give interpretable insights while maintaining good performance. Next, expert system concept and architecture. One of the earliest form of AI applied to power system is the expert system. It starts with a knowledge base. The domain rules and heuristics proved by experts. An interface engine applies logical reasoning using forward or backward chaining to arrive at decisions. Representations, often through if-then rules, ensures transparency and interpretability. The explanation module is crucial as operators must trust systems decisions, and finally interface modules connect real-time SCADA or PMU data to the expert logic. The system remain valuable in protection, diagnostics and operational supports. Next, brief history of artificial neural networks. Let's briefly look at how neural networks evolved. In 1958, the perceptron was introduced, the foundation of modern neural networks. In 1986, backpropagation made multi-layer networks practical. During the 1990s, neural networks gained traction in power systems. The major deep learning breakthrough came around 2012, enabling complex nonlinear learning. From 2017 onwards, advanced hybrid system and smart grid AI have rapidly expanded the role of neural networks in the industry. When we talk about data-driven models, we are primarily referring to three learning paradigms, each suited for different problems in electrical engineering. First one, the supervised learning is the most common. The object the objective is to map inputs to labeled outputs for prediction. This requires signals like historical fault logs and pre-labeled data. Key examples are fault classification and load forecasting. Unsupervised learning aims to discover structure or anomalies in unlabeled data. This is ideal when you have large unlabeled sensor datasets. It's used for anomaly detection or clustering of load patterns to find hidden trends. Finally, reinforcement learning. Its objective to learn policies via reward for sequential control. This requires environment model or simulator to provide a reward signal. Practical applications include adaptive inverter control and sophisticated demand response strategies. Next, before diving into modern AI, it's important to understand the traditional approach, expert systems, which are rule based. They are excellent because the advantages include being explainable and easy to encode safety rules directly. However, their disadvantages are significant. They are poor at generalizing to unseen or unexpected scenarios, may, making them brittle. The alternative is data driven models, which are the focus of modern AI. Their major advantage is higher accuracy on complex pattern and they are inherently adaptive. The trade-off is their advantage. They require label data which can be difficult to acquire and the models are often opaque and brittle, meaning it's hard to understand why they make a decision, which is a major challenge in safety critical electrical applications. Next is fault before and after fault detection accuracy. Our second application example is fault detection in protection systems. The baseline approach uses threshold based relays. The trade-off is they are slower response and are prone to false trips under noise, especially in dynamic grid environments. The modern approach is the ANN pipeline. This involves feature extraction from raw signals, feeding into a trained classifier, and then running online interference. The outcome is a game changer. Improved sensitivity, which means catching real faults better, fewer false positives, reducing unnecessary grid interruption, and ultimately faster classification for timely productive action. Next is before and after load forecasting error, pre or post machine learning. Let's look at two specific examples of AI impact, starting with load forecasting. The traditional approach uses seasonal ARIMA models or simple smoothing. While effective for base loads, has a limited nonlinear capture capacity. The machine learning pipeline is far more sophisticated. It involves data preprocessing, extensive feature engineering, followed by advanced models like LSTM or GBM. The results is a conceptual reduction in root mean square error and mean absolute percentage error, the key metrics for forecasting. Crucially, it provides a improved handling of renewables variability, which traditional method struggles with. The shift provides grid operator with greater confidence and less reserve capacity requirement. Next, we can categorize the application into five core areas. First one, the power system. Second one, control. Third one, electronics. Fourth one, communications. And fifth one, condition monitoring. For power system, AI is a vital for assessing stability, enhancing protection, and making accurate forecasting. A concrete example is using an artificial neural network for fault classification. In the control domain, we see adaptive control, model predictive control, reinforcement learning applied for tasks like inverter coordination. This is a crucial area for integrating renewables. Moving to electronics, AI assists in design optimization and signal denoising. For instance, genetic algorithms and machine learning are used for tasks like EMI prediction. In communication, AI help with channel estimation and anomaly detection using methods like convolutional neural networks for spectrum sensing. Finally, condition monitoring. We use AI for fault detection and predictive maintenance using autoencoders and other ML techniques for failure prognostics. Next, designing a AI workflow for electrical engineering problem. A successful project requires a structured, safety-aware workflow, which we can break down into six sequential stages. Stage 1, problem definition. The absolute first step is to specify the objective constraints and safety requirements for the electrical engineering application. In stage 2, data acquisition. This involves collecting SCADA, PMU, and sensor data along with necessary labels and metadata for training and validation. In stage 3, modeling and training. Here we select the AI paradigm, architecture, and validation plan that aligns with our system assumptions. In stage 4, validation. This is where we ensure robustness. We apply techniques like time split cross validation and targeted stress test. In stage 5, deployment. A critical decision is edge versus cloud interference. We must verify latency and reliability requirements to ensure real-time performance. Finally, the stage 6, monitoring and retraining. Post deployment, we must continuously detect data drift, schedule necessary updates, and maintain safety and traceability in all our model versions. Next, data considerations, signals, labels, and noise in electrical engineering. The success of any AI model hinges entirely on its data. We need to consider four key aspects. First one, the data types. We rely heavily on time series PMU data for high resolution measurements. We also use spectral data via fast Fourier transform for frequency domain analysis and sometimes images for thermal or drone inspections. Second one is sampling and synchronization. High resolution data like PMU must be synchronized at rate like 30 to 120 samples per second. Timestamps must be precisely aligned for multimodal data fusion. Third one, labeling strategy. Real world labels are often scarce. So we use even logs and simulated faults for ground truth. A powerful technique is physics-based simulation augmentation to generate synthetic yet realistic training data. Fourth one, noise and anomaly handling. Electrical system are noisy. We must pre-process with filtering and outlier detection. and then train models to be robust, often using a robust loss function and augmenting our data with synthetic noisy sample. Next, evaluation metrics and validation for electrical engineering AI models. How do we measure if an AI model is good for an electrical engineering task? We use specific metrics and validation schemes. For classification problem, like fault detection, we use precision recall F1 score and ROC or AEC curve. In our domain, recall not missing a critical fault is often prioritized. For regression problems like load and voltage forecast, we use RMSE and MAPE as we discussed earlier. Our validation scheme must account for time. We use time split validation, rolling windows, and critically scenario based stress test to ensure the model handles extreme events. Finally, we have unique domain constraints that supersede pure accuracy. This includes strict measures, latency adherence to safety threshold, and managing worst case failure rates. Next, risk assumption and common pitfalls in electrical engineering AI project. To conclude our overview, let's frame that the challenges using SWOT analysis for electrical engineering AI project. Our strengths are the primary drivers, improved detection and optimization capabilities. Our weakness are critical constraints, data scarcity, for rare faults, which makes training difficult, and model opacity, the lack of explainability. The opportunity represents the we can integrate PMU or IoT data for truly sophisticated predictive maintenance and optimization. Finally, the threats, the risk we must mitigate, including data drift, where real world conditions change post deployment, sensor bias causing systematic errors, and the danger of safety critical failures due to model mistakes. Mitigating these threats is the fundamental challenge of building safe and reliable AI in electrical engineering. Next, tools and the techniques from simulation to deployment. The workflow relies on a practical stack of tools and the techniques. We can map them across four layers. The layer one, simulation and modeling. The role here is to build grid or plan digital twins and generate physics-based scenario data. The technique we use is co-simulations for contingency scenarios. In layer 2, signal processing, the role is feature extraction, including processing raw sensor data, techniques including wavelet transforms for transient detections and simple filtering. In layer 3, machine learning frameworks, the role covers training, experiment, tracking, and validations of the core models. The technique is using enable models and method for uncertainty quantification uh, to provide confidence score. Finally, the layer 4, embedded deployment, the role is edge interference, real-time constraints under quantization. The essential technique here is model compression and latency testing to ensure the model runs quickly on embedded hardware. We have covered a lot of ground today, from core applications and data challenges to specific workflow and validation methods. Let's summarize the actionable takeaways and outline the next step for applying AI in your engineering practice. The first key takeaways, AI fundamentally improves forecasting, protection, and control across electrical systems. However, its successful application is completely dependent on data readiness, having the right high quality data, and maintaining a sharp safety focus. Second, the immediate actions you can take today, start by conducting an internal audit. Map your specific electrical engineering use cases to AI suitability. Audit your existing data quality and availability. Then run small pilots on Non-critical systems ensuring robust monitoring is in place from day one. Third one, the learning resources to advance your knowledge. Dive into technical literature on AI and power system. Gain experience with the domain simulation to generate synthetic data. And finally, get hands-on with the data set and use safety checklist to build confidence in reliable deployment. Finally, the essential pillar of governance for any large scale deployment, you must define validation standards specific to your engineering constraint, address explainability needs. We need to know why the model made a decision and always ensure rigorous regularity compliance. AI is a powerful tool, but it requires discipline, domain knowledge, and a robust, safety conscious workflow. Thank you.